Okay, can everybody hear me? Excellent, excellent. So before I begin, I'm sorry, but I have to take the obligatory speaker selfie. It has to be done in front of this amazing audience. So everybody say hello. Hey! Okay, welcome to this Micronaut deep dive. Fantastic to have all of this room full, almost, and all these folks interested in Micronaut. Hopefully this talk will be giving you the information you need to take away and see what Micronaut is all about. For those of you who don't know me, my name is Graeme Rocher. I am the creator of a couple of relatively well-known frameworks for the Java ecosystem. One called Grails. Who's heard of Grails here in the audience? Quite a few. So, and of course, Micronaut. I'm an engineer at a fantastic company which contributes significantly to open source called Object Computing. In 2018, I was privileged to receive the first Oracle Groundbreak Award for the work I did on Grails. I've been working on Java frameworks for like over 12 years now. Pretty much know how they work, and was recently nominated as a Java champion as well. So that's me. So on the agenda today, we've got a pretty packed agenda with lots of things to cover, and we're going to sort of split it out into 4 parts. In the first part, we're going to do an introduction to Micronaut. We're going to talk about why Micronaut exists. We'll go through Micronaut fundamentals, how to write tests with Micronaut, how things like bean introspection, which is a pretty fundamental feature of Micronaut, works, dependency injection and configuration management, kind of the core dependency injection container stuff and how all of that works with Micronaut. In part 2, we'll be looking at how Micronaut's aspect-oriented programming APIs work in AOP and how all that fits together, how that feeds into to enable features like bean validation, bean event listeners, and so on. Then, I'm sure for some, mercifully, we'll have a 10-minute break where you can go relieve yourselves or do whatever you need to do for 10 minutes. And following that, we will get right into the more servery HTTP REST side of Micronaut and how that works, the HTTP server, the HTTP client, the filters, service discovery, how it works with Swagger. And finally, in part 4, we will have a brief introduction to a new project that's part of the Micronaut kind of ecosystem, which is Micronaut Data. And we'll look at how it works with JPA, JDBC, and also integrates nicely with GraalVM native images. So let's get starting straight away with part 1, with the intro. So, you know, when we started building Micronaut, I think it was like 2.5 years ago, we had been looking at these kind of problems that Java frameworks face, any framework developer faces. And we wanted to build a framework that addressed these problems head-on and didn't make the same mistakes. So building on that kind of 10 years of framework development knowledge, what can we do to address these problems that were so complex for framework developers, and are also complex for users, because that complexity at the framework level feeds into the user code. So things like the limited annotation API in Java. Java has annotations, but they're very much limited in terms of there's no APIs to discover what annotation is annotated with another annotation, like meta annotations. Annotation inheritance, where you have to inherit when you inherit annotations from a superclass or a super method. Works, a bit hit and miss in places. There's no real ability to merge annotation metadata from different sources. And there's no built-in way to scan for annotations on existing classes and look for the particular class annotated with particular annotation. Type erasure is a nightmare for everybody in the framework community. Anybody who's built a Java library, the fact that this thing has declared a list of string in this field, but then at runtime, it's not a list. It's gone. The information is gone, and there's all this framework code that you have to write to use like parameterized type, and it works differently whether it's a field or a method or a constructor or a type erasure is a nightmare. Reflection generally being slow, which has implications. People have written all sorts of complex solutions to solve this problem in terms of using bytecode generation at runtime, trying to do direct method invocation, to use things like invoke dynamic as another path you can go down. And then the fact that reflection is relatively slow to retrieve and relatively slow to execute, there's this proliferation of reflective data caches. So, if you're thinking about a typical Java application that's been built over the last 10 years, you have like a reflective data cache, and what I mean by a reflective data cache is a cache of like method references or field references. You have one for Hibernate, you have one for Jackson, you have one for Spring, you have and they don't share it. So you have all these caches of all this reflective data all over your place, and it just expands your memory use. And when you add that to then class path scanning, which is pretty slow. The fact that Java applications are pretty dynamic, and dynamic class loading can add complexity and slow down your app. All these issues led to the kind of having to balance how we built the internals of frameworks, so we didn't end up with class path scanning that was too slow, or dynamic class loading that was too aggressive, or URL class loader problems and so forth. So. And there was this, there's this relationship generally between most Java frameworks out there today, where you have this relationship between the number of lines of code in your code base and your startup time and memory consumption. So as your project gets bigger and bigger and bigger, as do your requirements for memory and in terms of your app. And it's been very typical, in fact, in the past 10 years to see large Java applications that occupy gigabytes of memory, a lot of this is down to the way that frameworks are designed, and a lot of people arrive to this decision point where they kind of had to make a decision about whether we go for a kind of more like a do-it-yourself toolkit, which these frameworks are awesome. Vertex is awesome. They have their place, but they're very much do-it-yourself kind of toolkits. You put them together yourself, versus things like Spring and Grails and so forth, which have much more opinions and much more productivity benefits. And it was a shame when we started looking at building Micronaut that there was this choice where if you wanted like low memory consumption and the best performance, you had to go to these kind of do-it-yourself toolkits. And if you went to the top right corner, you ended up having to sacrifice either startup time or memory performance or all sorts of things because of the complexity of the frameworks themselves. So we wanted to address this imbalance with the design of Micronaut by creating something that was didn't suffer from the low memory consumption, doesn't suffer from the high memory consumption and high startup time problem, and but it wasn't a do-it-yourself toolkit. Still had the same rapid application development feeling as something like Spring or Grails. And the reality with microservices is that frameworks that are based on reflection and the architecture of using reflection annotations become fat. They become fat in terms of memory consumption. In particular, we love the programming model. We love majority of Java developers out there love the Spring programming model, the Jakarta E programming model, and they love the way that works. They're just are not enamored with the amount of memory consumption that results in, or weren't at the time when we started building Micronaut. And the question what we asked ourselves is, why can't we be more efficient? Because Java's problems, in general, for microservice are greatly exaggerated. People have been stating that Java has been dead, forever, and Java can be very fast. The fact that I know it's not the normal virtual machine, but the fact that it's used as the language for Android, which has similar requirements to microservices in terms of wanting low memory footprint, fast startup, is testament to the fact that Java is very flexible and can be used in a number of different scenarios. The problem is that historically, in the last, over the last 10 years, the frameworks and existing tools that are built on top of Java leverage techniques like reflection, runtime proxies, and runtime bytecode generation, whether it be through something like ByteBuddy or cglib or something like that. And building a framework based on those techniques leads to higher memory consumption. Why does it lead to higher memory consumption? Well, why is reflection a problem? And lucky, that's not a difficult thing to identify. You can have a look at why. This is referencing the JDK8 class, but it's the same in any version of Java. The actual functionality is the same. The reason is that as soon as you access anything reflectively in Java on a class, whether it be a field, or whether it be a method, or whether it be a constructor, doesn't matter. As soon as you access one item reflectively, it initializes all of the reflective data for that class. So now consider that for a moment. Say you've got a class that's got like 100 methods, or a dozen fields, and you've got one @inject statement, for dependency injection on a constructor or on a method. The fact that you have to pay the cost to store in memory every single reference, every single field, every single method for that class is a real shame, right? You're loading all of that reflection information, all of the java.lang.reflect.method, all of the java.lang.reflect.fields, and where they get stored is they get stored in soft references. So for those of you who are unfamiliar with what soft references mean, soft references essentially mean that the references to that reflective data will not be garbage collected until the Java virtual machine is running low on memory. Right? So there's no way to reclaim those methods. And because we end up with different reflective data caches, one for Jackson, one for Hibernate, one for Spring, one for whatever other library that you're using is using reflection, you end up with all these method references all over the place, all these field references, all over your code base occupying memory, because they all get initialized, which is the lesson we learned from this when we were building Micronaut is, if you want to achieve low memory consumption, you really have to avoid reflection. You can probably achieve low memory consumption for a Hello World app or a very small app without, if you do use reflection. But as your code base grows, you will undoubtedly use more and more memory. And there's no real way around this with today's limitations on how reflection is obtained in Java. Looking at the design of Micronaut, when you started looking at how to build it, many of the existing Java specifications from Java EE at the time, now Jakarta EE, even mandated the use of reflection. Some of the AOP APIs insisted that you receive a java.lang.reflect.method. We've actually had some feedback from people, a number of people saying, why does Micronaut not use XYZ Java specification? Well, we would have loved to have used that specification, but we would not be able to be spec compliant because we don't use reflection ever, anyway. And this is pretty much the direction the Android community has already headed into and has headed into for some time. Android has used ahead of, the Android tooling has used ahead of time compilation extensively for some time. Things like Google Dagger, which is the sequel, I guess you could say, to Google Juice, which is a dependency injector for Java that uses annotation processes and doesn't use reflection. And if you look at most Android frameworks and tooling in the mobile space, very few of them, if any, use reflection anyway, for obvious reasons, because it's slower, and it consumes memory, which is not acceptable on low memory footprint devices, potentially. So Micronaut, Micronaut. What is Micronaut? Micronaut is essentially a microservice and serverless focused framework, hence the name. You could probably imagine that. But it's also a complete application framework for any kind of application, really. So, you can use it to build microservices, and of course, that's what we are encouraging folks to do, because that's what it's designed for. But you can use it to build a whole bunch of things that are not microservice related as well. It essentially features a core that's based on dependency injection, aspect-oriented programming, and configuration management. It's kind of the core part of it. And all of those APIs, all of those features are completely reflection-free. And you can build with Micronaut microservices. You can build. It's getting very popular in the serverless space for building. It has integration with AWS Lambda, and you can build serverless applications. We have a lot of interest from the Kafka community in particular for building message-driven applications. So we have nice Kafka integration, and a lot of folk are writing headless Java applications that don't have a server, just listening to streams of data from Kafka or RabbitMQ. You can use it to build CLI applications, so just command line applications. And you can even use it to build Android apps. So we have the core of Micronaut and the Micronaut HTTP client working already on Android. And you can share a client on the Android side and the server and write the same logic and share a fair amount of code between server and client. So we have it working on Android. And anything pretty much that has a static void main is Micronaut compatible. So like I said, in terms of history, Micronaut, we actually started working on Micronaut over 2 years ago. We were working on it in a non-open source manner for well over a year. We open sourced it in May 2018, and it's been creating waves ever since. It's inspired a whole bunch of frameworks which we shall not name names to improve their performance, so that existing frameworks out there are getting a whole lot better. And it's also inspired a whole bunch of new frameworks, again, we shall not name names, to be born based on a similar approach. And it's really changing how the expectation Java developers have of how a server-side framework should perform in terms of startup time, memory consumption, and general overall performance. So the current status of Micronaut is that we have a 1.25 release out there, which is this current stable release. It's built by the people that built Grails, like I said. It's reached nearly 3K GitHub stars, which, by the way, I have some Micronaut t-shirts to give away. So at the end of this talk, I think we're close to 3,000. So if you go logging into the GitHub, if you have a GitHub account, go and star the repo, and then I'll look at the end of the talk and pick some random names. I don't have enough t-shirts for this whole room, obviously. That would be problematic. But I'll pick some names from the GitHub, from the latest stargazers, and at random, i.e. eeny, meeny, miny, mo. And no complex algorithm, just be eeny, meeny. And I'll give away some t-shirts for anybody who has started during the course of the presentation. And it's used in production already by a whole bunch of companies, delivering real savings, particularly in cloud spend. One of the biggest feedbacks we've had from our customers is object computing, is how much less they're spending. We have a whole bunch of GCP, Google Cloud customers, and they've seen their cloud spend drop significantly because the fact that Micronaut server processors are using such much fewer resources in terms of memory, and they're able to deploy much smaller processes and containers. So who's using Micronaut? So these are some of the names out there that are already using Micronaut out there. This is all on our website. Some of them you may have heard of. I'm sure most of you probably have heard of Minecraft. Probably the biggest game in the world. They're using Micronaut. Target, a big US chain, consumer chain. smart things from Samsung. So yeah, a whole bunch of existing companies. These are the only ones I could name that could get permission. Getting permission is challenging from our customers, but these are some of them out there. And I'm sure there's a whole bunch more, given the interest in Micronaut has been in the last year. So, in terms of those problems I talked about earlier, so what solutions does Micronaut offer to those problems, and how does it implement those solutions? So, in terms of a limited annotation API, what Micronaut does is it pre-computes the annotation metadata at compilation time. So, Micronaut is all about moving your processing away from your runtime into your compiler. So at compilation time, it pre-computes what we call annotation metadata for every single every case where the framework needs annotation metadata, whether it be on a particular class that is annotated with a particular annotation, or like an at controller or an at or a method, for example, like at get, and it pre-computes. In addition to that, arguments type, generic type arguments, because actually, when you look at the source code, when you're analyzing source code of Java, the types are all there, remarkably. They just get erased at compile time. So we're able to pre-compute all of that logic to produce the actual argument reference, which contains all of the type arguments, and not have to worry about type erasure like traditional frameworks do. In order to avoid the slow reflection problem, we eliminate reflection completely. In order to deal with reflective data caches, there's no data caches in Micronaut itself, so we don't cache any reflective data anywhere. And in some cases, we also patch existing libraries. Like for Jackson, we have written a module for Jackson for JSON marshalling that is reflection-free and uses Micronaut's introspection stuff, so that Jackson doesn't use reflection either. There's no class path scanning in Micronaut, so we don't scan any class paths. There's also no dynamic class loading. It's just a main method, system class loader. We don't have any dynamic URL class loaders. There's no weird class loader hierarchies. And no weird class loader issues to deal with. So, I like to think about Micronaut as an intelligent compiler. And for me, I think the general industry trend and industry direction where things are going in the Java space at the moment, and this is not specific to Micronaut, is that the future is essentially more intelligent compilers and smaller, leaner, faster runtimes. By doing less at runtime, Micronaut's runtime is much smaller than most other frameworks. Whilst on the other hand, its compiler is more complex, without doubt. But that's a trade-off I think that's worth paying, because you're able to achieve smaller, faster, and more efficient applications. Okay, so now that's quite a bit of talk. Let's actually do some coding and demos and see how we go. And before we get going, I want to talk about how a Micronaut project is structured. So I've got a minimal application here, which I will enter presentation mode. This is a minimal application, and I call it minimal because this is the absolutely minimum amount you need to get going with Micronaut. So it's just in terms of a Gradle build, and I've got both a Gradle and a Maven build here. But you can see all I've got is the Java plugin. And the only difference between this application and like a normal Java application is the declaration of an annotation processor, which is called Micronaut Inject Java. So Micronaut Inject Java is an additional annotation processor that we use to visit your code and generate additional classes to support the framework. And if you want to see how that looks in Maven, Here's the equivalent POM. Again, this is a minimal Micronaut application where I'm using Micronaut's BOM for dependency management. And then I've got a compiled dependency on Micronaut inject. And the only other thing I've got in here is down here is the Micronaut inject Java annotation processor set up in my in the Maven compiler plugin. You have to supply annotation processor paths. So we've got a Micronaut inject Java annotation processor. So the nice thing about tools like IntelliJ, and one of the nice things about using annotation processors, is that the tooling out there today, like IntelliJ, like Eclipse, like Visual Studio Code, already understands annotation processes. So this means that there's actually really little tooling that you need to use Micronaut. In fact, there's not a great deal of tooling you need for Micronaut because it's just a compiler plugin and so forth. And all the existing tools already understand it. So you know, with just those two things in there, I can already compile and build this application, and that is, you know, if you want to get going quicker, like you don't have to manually create your build file, we do have a command line interface. So it's available by SDK man. So you can type within a bash shell, for example, SDK install Micronaut, and that provides an mn command, and you can do create app, and then the name of your app, in this case example, and you can specify what kind of build you want, whether it be Maven or Gradle. We support both. So the CLI part of Micronaut is not required to use Micronaut. It's a handy helper to get going, just a code generation tool, but it's not a required part of Micronaut to use it. I do find it handy though for creating quick apps and getting going quickly. So like I said, the minimal setup for using Micronaut is declaration of an annotation processor, which is Micronaut inject Java, which you can declare in either Gradle or Maven. And how it works is that Micronaut inject will visit your source code. So for example, in this example here, we've got a class that has @inject and some other bean. And it will generate an additional set of classes. So it generates bytecode in the same package as your class, as synthetic classes. So in this case, this is pretty much pseudocode, but you'll see that you'll get a class called myBeanDefinition that extends abstract bean definition, and it will have a build method which constructs the bean and sets other bean to retrieving the bean from the context. And these classes are generated at compilation time automatically for you. They're bytecode. You can look at them if you want. IntelliJ has a decompiler which you can open, but they're considered internal parts of the framework. And by using this approach, we achieve a couple of things. One is, you can see, we can construct directly the bean definition. So you can see that the bean definition here is being newed up directly. We can assign directly the field to another bean, and we don't have to use reflection at any point in time. So throughout this whole talk, this whole deep dive, I'm going to be using a library called Micronaut Test. Micronaut Test is, you can get to it at that link, github.com/Micronaut project/Micronaut Test. And it's a single dependency that works either with Spock or JUnit 5. So in Maven, you can declare it that way. And if you're using JUnit 5, and in Gradle, you can do it the other way. And essentially, it adds an annotation called @MicronautTest that helps write tests a bit easier with Micronaut. Actually, Micronaut itself is not difficult to test without Micronaut Test. If I wanted to write a test here without the use of Micronaut Test, what I could do is create a example test, like this. And it can be a JUnit test. And you would have something like before, or before all, probably. Micronaut .run context. You basically have a startup hook, and after all, static void cleanup hook that closes the context. So that's how you would, if you were not using Micronaut test, that's essentially what Micronaut test does in a nutshell. It sets it up and injects your test. Because Micronaut's application context, which you can see that I've spun up here, implements auto-closable, you can even do something like application context.run inside of a try with resources block, and then retrieve beans from the context directly in that way. But Micronaut test is very, very convenient. So instead of having to write that little, very minimal plumbing code, all you have to do is add an annotation on here that says Micronaut test. And your test will automatically spin up the context and shut it down, which cleans up a whole bunch of ugly stuff that we don't have to repeat in every test, which is good for code reuse. It's a JUnit 5 extension annotation, and it works with Spock as well. So since I'm going to be demoing a lot with Micronaut test, I wanted to make sure we introduced it early. Basically, you can say at Micronaut test and at inject on your test itself, a particular bean, and then write your test as usual. So let's start with one of the fundamental building blocks of Micronaut, which is bean introspections. So bean introspections are fundamental in any framework out there. Bean introspections have typically been exposed via the introspector API. So in Java, there's this introspector, java.beans.introspector, and many frameworks in the past have been based on this, where you would call get bean info, and if I had for example, pet class here, that had a name or something like that, and a couple of getters, getter and a sitter, there we go. If I could come in here and I can say get bean info pet class, and from that you could then get hold of the property descriptors for the properties of that bean and iterate over them, and do general bean introspection stuff. So this introspector class has been part of the JDK a long time. Many frameworks were based on it in the past, and as you can imagine, it's based on reflection. And as you can imagine as well, it's got yet another reflective data cache. In fact, several reflective data caches that cache the reflective data in soft references. So, to start building a framework where you need to, introspect beans, and, when we talk about introspecting beans, we want to be able to set and get properties of existing beans. That's kind of a fundamental feature of a framework, to be able to analyze your classes. So, for example, in this class, we've got a name property of this pet. So in order to do that with reflection-free with Micronaut, what you can do instead of doing all this stuff and using the bean introspector is you can just come into your class and you can add at introspected onto the class itself. Then you can come in and here and you can say bean introspection, and it's a bit more of a modern API where you can say pet.class, and there's my introspection. Yeah. So And with that introspection, you can then say, instantiate to create a new pet. And you can say do things like introspection.get required property name, which is going to be of type string. So we have an ability to get a reference to a particular bean property. And you can do things like property.set pet, some name, and then if we output that pet.get name, you'll see that the actual bean introspection gets set. I suppose if I would have to add a test to that. So there you go. You see that in my output here, it's outputting some name. So you can see with a bean introspection, the value of a bean introspection in Micronaut is that we can instantiate beans, we can set them and we can get them, and we can do all of that dynamically without using reflection. So when does this come into play? This comes into play, for example, when you are marshalling an object to JSON. Or you want to convert an object to JSON, you need to iterate over its properties. You need to read the properties instead of doing set, you need to read the properties dynamically by saying a property.get to get the value it, and you need to write those objects to JSON. You need to get the property names. So in this case, bean property, you can get the name of the property from it. So that's my property name. So bean introspection allows those kind of use cases. Another example is reading objects from the database, like with a tool like, for example, Hibernate, which reads an object from the database, and again uses reflection to introspect the properties, reads and writes them to your objects, so you can map essentially a row in a JDBC result into an object. So this kind of dynamic behavior is required, and we wanted to build have as a fundamental building block. To Micronaut the ability to read and write bean introspections. So you can see that as I run these tests, if we look at my output, which is actually in the test directory, we've got my pet class, we've got my and in addition to that, Micronaut generates a additional introspection.class. You see how this is how Micronaut works, in that it generates additional classes that sit alongside your existing classes. So at no point does Micronaut ever modify your bytecode. It doesn't transform your bytecode. It doesn't modify your bytecode. It generates an additional set of classes that sit alongside your bytecode, and that include things like the ability to a bean introspection in this case. And the bean introspection that I retrieved for pet can be used for lots of things. We also have a nice wrapper, simpler ways to do this as well, which is called bean wrapper, which you can say wrapper, bean wrapper, and get hold of a wrapper. And then you can do things like set property, name, some value, which makes it a bit easier. Get property, that should be a string. Or else. So bean wrapper is like an abstraction above the bean introspection API, where you can wrap an existing instance of an object and get and set properties on it. And throughout the whole thing, at no point is Micronaut using reflection anyway. So if I were to, for example, come into my pet class here, pet, there it is. And if you were to set a breakpoint on that, content breakpoints. There we go. If I were to set a breakpoint on that and a breakpoint on there, and run my test again with my breakpoint set, you'll see that the actual stack trace where I'm setting setting the property on my bean is not using reflection at any point. It's directly invoking your set name method. So bean introspections are a pretty important part of the way Micronaut works. And I'm going to open another window here because I want to switch to a more complete application. So okay. So I've got this other application which has got a few more dependencies. And what I'm going to do is create that pet class one more time. And I want to demonstrate to you the importance of bean introspection annotation metadata and why it's important from a Micronaut perspective. So, in a lot of frameworks out there, for example, bean validation, you can do things like have an annotation that says not blank, that applies a constraint here on this field, and that says that that field cannot be blank. Notice how that the annotation itself is on the private field, yeah. And you can also have another annotation on the method. This is going to be called min, say 20. And you can see that now immediately I have an annotation metadata problem. I have several problems from a framework developer's perspective. If you're building a framework, the first problem is that the not blank definition in my validation constraints here is on a private field. So in order to actually figure out that that's not blank, I have to reflectively go into the class. I have to get the declared field and potentially break the module system, encapsulation, all sorts of things, because you have to get hold of the private field, make it accessible. Potentially, you basically have to look into the private members of the class at runtime. And also, frameworks like bean validation allow you to declare constraints, in this case I've got two not blank and size, on both the field, but also on the getter in Java, right? So suddenly I have to do things twice. I have to look at the field, and I have to look at the method, and I have to merge that information into a single view because it applies to one thing. So all of these things ended up being a annotation metadata problem. That's one of the things that Micronaut really does simplify from a framework developer's perspective, is that I am going to make the font size a bit bigger for you guys. Is that you can you can get hold of the bean introspection, and I can say bean introspection.get, get my bean introspection again, and I can get hold of the property, in this case name. So that's going to get hold of my bean property. And what I can do is I can do things like do this kind of query, bean property.get annotation values by type. And I can say constraint, right? Get annotation values by type. And that's going to give me my values. And I can iterate over those, and that's going to be an annotation value. And I can say, system out annotation value dot get name. So if I were to run this example in my test it. Hold on, I need to make sure I have annotation. So if you see this error, which says you need to make sure annotation processes are enabled in IntelliJ, where it says Micronaut test used on a test but no bean definition is present, that means that the annotation processor was not enabled for this project. So I'm going to rebuild it. Okay, so values by ship. Annotation names by stereotype. Sorry. Names. Okay, run that again. And you can see that in this case, I'm doing a query on the bean property that's saying, get me all the annotation names that are annotated with a constraint. So Java out of the box doesn't provide anything like this, where both not blank and size are both annotated with constraint. Yeah, they are themselves annotated with another annotation. So there's nothing in Java that allows me to do this kind of query, and this is something that frameworks have to roll themselves, and they have to roll it at runtime. Yeah, so you have to perform all this analysis, this reflective analysis on the types, on the properties, on everything at runtime to figure out this kind of use case. When in Micronaut we just compute it at compilation time, so that I can say, for that particular property, get me all the annotation names that are annotated with a particular stereotype, in this case constraint. From the name, you can then say, get property, get string value, name, some member. It could be whatever, min or something like that, to get a value of a particular member. So we have this API that allows you to query the annotations without loading the reflective data or without requiring a reflection. All of this is available and is pre-computed at compile time. So that's a critical part of the way that Micronaut works. So introspected is a key fundamental building block of Micronaut. It's an AOT reflection-free replacement for the bean introspector. Set get bean properties, create instances. You can it includes the annotation metadata, so I can analyze the annotations, and you can do things like instantiate the bean itself, get a reply property, and read and write bean properties without a reflection. And in Micronaut, we've plugged this into Jackson, like I said, so that JSON marshalling does not use a reflection. The annotation metadata itself is, again, it's pre-computed at compilation time, so that we don't have to do the analysis at runtime. It includes knowledge of meta annotations, so that you can visit, figure out particular annotation stereotypes, or get all the annotations annotated with another type. And another important thing, and you probably have noticed that I'm really focusing on annotation metadata and how important it is in the way that Micronaut handles it. But we allow things like at compilation time to map the value of one annotation to another. And so to demonstrate that, I'm going to, I have a demo prepared here, which I'm actually going to shorten because this is, we still have a lot to go through. So what I have here is an example app, which I'm just going to revert some changes here. So I've got an example application here. In this case, one of the criticisms we had from some folks regarding Micronaut is that we don't support JAX-RS annotations out of the box. And one of the reasons why we didn't choose to go down the JAX-RS route out the gate is because we didn't want to couple ourselves to any particular annotation model. Now, that decision, in hindsight, proved to be the right one, because the decision from the Jakarta team group is that JavaX dot is going away and is being replaced by Jakarta dot. So the fact that we didn't support JavaX out of the gate was actually the right decision in hindsight. But one of the nice things about Micronaut, and the reason why it's so powerful in the fact of treating handling annotation metadata at compile time is because we can easily add support for another annotation model. So I've got an example here, which is it's a multi-project build. It's got two projects. One is the JAX-RS processor project, and another one is an example. And it has a hello controller, which is annotated with JAX-RS annotations. What it does is it just says hello and then outputs a message. And I'm going to revert that as well. And in the processor itself, what we have is a couple of classes that integrate with Micronaut. So one is a type element visitor. So Micronaut allows you to hook into the compiler so that you can, at compilation time, visit your source code. And this is a really powerful feature of Micronaut. This is a type element visitor. And what it does is, at compilation time, this visitor is going to be triggered for every class that is annotated with @path. So @path is a JAX-RS annotation. So you can probably imagine now that this class is annotated with @path. So what's going to happen is the compiler is going to visit this class at compilation time, and it's going to call the visit class method, my method that I'm writing. Within the context of that method, I can then, using the class element, which is part of Micronaut's AST API, which allows you to plug into the compiler. And it's important because Micronaut supports Groovy, Java, and Kotlin. So it doesn't matter what language your developers use. This visitor will work with any of those three languages. And what it's going to do is it's going to, every time it encounters a @path, JAX-RS @path, it's going to dynamically annotate the class itself with Micronaut's @controller annotation. So Micronaut controllers, like I said, don't use JAX-RS. They use @controller. So instead, we map path to @controller by dynamically annotating it. So that's one part. And then I have another part, which is what's called an annotation mapper. So Micronaut supports two notions. One is annotation mapping, which is mapping the value of one annotation to another annotation. And another is remapping, which allows forgetting the previous annotation and remapping it to another annotation. This is an annotation mapper that looks at the JAX-RS get annotation and maps it to Micronaut's version, which is also called get at compile time. So the reason why this is so powerful is because all this work is being done at compilation time. So there's literally no runtime overhead for Micronaut. For Micronaut, it's just the same. It's just seeing the same thing. So with just these two classes in place, and another one that handles path on a method that maps path to HTTP method mapping, maps annotations, I'm able to get this example. Obviously, this I put together in like an hour. It'll probably take a little bit, a couple of hours at least to add full JAX-RS support. Give me some time. But essentially, Micronaut, with this change alone, Micronaut is able to interpret the JAX-RS annotations set and support JAX-RS annotations. Where, hey, that criticism goes out the window. So, and what's cool about this is because the runtime is not coupled to the annotation source code DSL, when the time comes that JavaX is renamed to Jakarta, it's just another set of annotation mappers. Yeah. So we're not going to put our Micronaut's user base is not going to go through a migration hell. It's just another we map this and it works the same as before. Everything happens at compile time. So that's why annotation metadata is so important. And as a bonus, you can even this is an example of Micronaut's HTTP client, which allows you to declare interfaces, and you can even use the JAX-RS annotations now, just out of the box with this example, to implement HTTP clients, which just works. So that's pretty cool. The fact that you can do that with Micronaut. You can map the value of one annotation to another at compilation time. And why is this so important? And why is annotation metadata so important? So I think the case of nullable in the Java ecosystem is the perfect case study of why annotation metadata is so important for Java framework developers, because there's so many of them. There's if you want to figure out if something is nullable, like whether it be a method parameter or a constructor parameter, you've got javax.annotation.nullable. You've got org.jetbrains.annotations.nullable, which is what Kotlin uses. You've got edu.umd.findbugs, which .annotation.nullable, which is the one from Spotbugs. And then Spring, for whatever reason, has their own version of nullable. So we've got all these nullable annotations. And if you're trying to write a runtime and you want to check whether something is nullable, what do you have to do as a framework developer? Do you have to write a check for every single annotation under the sun? No. Well, in Micronaut, what we do is we map all these annotations to just a single one. So it doesn't matter what annotation you use. At compilation time, it all gets translated into the same annotation, and you don't have these weird issues where nullable works for one annotation, or you import this one and then it works, but you import the other one and then it doesn't work, which ends up being a nightmare. So yeah, that is the Micronaut annotation metadata handling. So now we're going to look at dependency injection. So how does dependency injection work in Micronaut? Okay, so dependency injection in Micronaut is based on javax.inject. So essentially what you can do is you can just create beans. Like, for example, I can have a pet service here, and I can annotate it with @singleton, and it's going to can return a list of pet instances, like so, and this can be return arrays as list, something like that, new pet. Maybe we create a constructor for this argument. There we go. Fred, another pet, new pet. Bob, and that's my service. And then you may have a controller, for your web endpoints called pet controller, and that's going to be a controller which is going to expose all of our pets, and it's going to map to the get URI like I introduced before, and you're going to have a list of pet. Maybe this will be our index. This time we can use constructor injection, so I can have a private final pet service, inject it by the constructor, and we can do pet service list pets, and just return it like that. Then in my test, maybe we can have a pet controller test. Something like that, and this is going to be a Micronaut test, and we can inject the RX HTTP client, which is the default low-level client in Micronaut, and we can test list pets and see how this goes. So we're going to do current.retrieve. Here's your request. Get pets. Is it pets? Yeah. And it's going to retrieve an argument, list of pet. Do blocking get first. To pets.size. Right, so let's see how if that works. It doesn't. Why doesn't it work? Let's see. No value specified for client. Oh, yes. So that should be mapped to the root URI. Okay, so that passed. So there's a basic example of building a little app with Micronaut that uses a whole bunch of dependency injections. So, I've defined here a singleton bean, which, has a list pets method that returns, just hard-coded set of pets. I've taken it into and injected it using constructor injection into my pet service and into a controller, and I've written a test for it that is using the low-level client from Micronaut. And the low-level client is being injected with @inject, which is just the regular Java x.inject TCK inject method, inject annotation. So Micronaut is compatible with the Java x.inject TCK. And yeah, that is how simple it is. So in terms of, there's a lot more flexibility that can be had here. So obviously I'm using @inject in this case. In the test, I could have used @inject here instead. I could have said, @inject and injected the field. We don't recommend this approach because we can recommend always to use constructor injection and to have immutable objects as much as possible. But it is, some people do use field injection for some reason. I think it pretty much always is favorable to use constructor injection, which is what we're doing here. If you don't want to, if this is an external class and you don't want to, you can't annotate it with a singleton, for example. What you can always do is create a pet service factory. And this would be a factory class, and you can say @singleton pet service, my pet service, and you can return that as a new pet service. In that sense, probably I'll have to do a. I'll have to comment that out, and I'll probably have to do a rebuild. But essentially, that's how you would create a factory. So a factory is essentially a class that creates other beans. In this case, it's creating my pet service. Now, pet service could be an interface, of course. You could have, iPet service, whatever. There's different conventions for this, which pet service implements. Like so, and you could have that up in your interface, like so, and then in your factory over here, you could expose only your interface, and you could make this the primary implementation, as an example. The way you structure that is up to you. I think that's probably a fail now because I don't have a pet service bean anymore. So it's failing because there's no actual pet service bean anymore. I now have an iPet service bean. So I'd have to do that. And I'd have to change that to be interface-based injection. Now it's passing. So that could be the primary. You can have in terms of dependency injection, you can do things like I can have a test pet service, which is another singleton, and it can also implement iPet service. Maybe just return a empty list or something like that. And this guy, you can say, because it's in my source test tree, we wouldn't want duplicate pet services. You maybe only want this in the context of your test. So what you can say is @requires environment test, so that this pet service is only present in the test environment. And you can also say things like @replaces bean iPet service. So what that means is essentially this service will only be active for the context in the test environment, and it will replace the pet service implementation. So we also have support for things like so this is currently the primary, but it could be a named pet service, one whatever, and then you could have another one over here, 2, and then you have multiple in that other. In that case, if you do that, then you would want to determine in some way, like for example, you'd say this: I want the be named 1 to be injected. So again, qualifiers, named qualifiers, and so forth, all would work as expected. I expect this will probably fail miserably because I've made lots of changes. Anyway, it's a very flexible dependency injection system that's based on Java x.inject. Oh, I didn't mention you can add @post construct and @predestroy, so that you have the ability to essentially hook into the life cycle of them. It's completely reflection-free, and we encourage constructor injection. The application context, you can run it standalone, like I demonstrated before. The application context is like your bean context object, where you can run it, retrieve beans. It's the kind of entry point for running Micronaut applications, and it can be customized with application context.build. So I didn't really demonstrate that, but essentially what you can do is, if you were constructing the application context manually, you can do things like application context.build and pass in a list of your environments, other, staging, whatever. Start building it. You can say whether you want to deduce the environment. Micronaut will automatically deduce the environment that it's running in. So for example, if you run on GCP, it'll figure out that it's running in GCP, and the GCP environment will be available. That's handy in things like this example here, where instead of environment.test, you can say environment.googlecompute, and that bean will only be present in Google Compute. So you can disable that, and in that case, only pass in here environment.gcp, and it will run only in Google Compute. You can customize a whole bunch of things, like what the main class is, add additional properties, and that you may want. And when you're done, you say build, and then start to start it up, and that'll start up my application context. So the application context object is like the entry point into starting and creating a Micronaut application. So it's the entry point. It's auto-closable, so you can shut it down. And bean definition is the interface that you interact with if you want to analyze a bean definition yourself. So within the context, you'll for each annotated object in your Micronaut application, in this case, I've got a controller, I've got a service. You will have a bean definition, and you can retrieve the bean definition and analyze it in whatever way you want. If you want to have some custom use case or whatever. I'm going to clean up this project a bit so that I can get test running again. So delete that. Pet controller. Right. Delete that. Okay. Project rebuild. Okay. So bean definitions are produced for any singleton, any factory bean, and it's fully JavaX.inject spec compliant. We also have support for configuration properties. So this is one of my favorite features. So well, this along with each property. So you can if you had a pet configuration class, Java class, pet configuration, and you can have configuration properties, and there's pets, and then maybe you have something like I don't know, max age or something like that. Maximum age of the pets has to be 20 or 50. Maybe that's pretty old for pet. I don't know. And getter and setter. That you can essentially bind this object into a from config. So to see that in action, what you can do is I can add to Micronaut test here something like another property called pets.max age, and the value is I'm going to change it to 50, and then I'm going to inject my pet configuration like that, and I'm going to test that. And we expect it to be 50, I believe, and that the demo guards are in our favor. So let's see if that actually fails, because client, I delete something. Oh, well, delete that. Delete. Okay. Okay, so that passed. So Micronaut test has a nice feature where you can set properties for the context of the test. So I'm setting the pets.maxAge property to 50 for the scope of the test using add property. You can also do it for the scope of the method, so I could put it on there, and it would set it just for the scope of that method and then reinitialize, refresh the context, essentially. So that's it's a nice way to inject configuration. I don't know what I did there. But essentially, but in addition to that, what's even cooler is the ability to handle like distinct configurations. So instead of at configuration properties, you can say at each property, and so now I'm going to instead of pets.maxAge, I'm going to say pets.maxAge1 and pets.maxAge2, and this one is going to be 100, and I'm going to inject at named 1. See, that passed. And now if I inject the second configuration at 2, then I would expect my second config to have a 100 second config, like that. There you go. So now I've got 2 configs. So that's the difference between configuration properties and each property. At each property, I can have multiple nested name configuration where each parent configuration is another one. Now, obviously, I'm hard coding these in here, but what I should probably point out is like typically you would have these in here. So you would have pets 1, max age 50, 2, max age 100. So you would have your configuration externalized into YAML or into the environment. Oops, what did I do? I don't know why that's not working, but it should be working. So probably I have to, maybe it's a copying issue with IntelliJ. No, I don't know. But, I'm modifying target classes. That doesn't help. Oops, modifying the one. It's the problem when you have so many like build tools and things flying around. Okay, now it passes. So I was modifying the wrong source application.yaml, but essentially, yeah, you can have multiple different config objects. And when it gets really cool with Micronaut, and when it gets really like this is one of my, like I said, one of my favorite features, is when you start driving. Typically you have a configuration object, and then you have a bean that uses a configuration object to do something, whether it be a data source or something like that. So you have like a pet configuration, I don't know, pet server, well, something, doesn't matter, configuration consumer. And over here, what you can say is for each bean that exists, so for each pet configuration bean, I want to receive this configuration, and I want to receive the pet configuration and do something with it. So you can. So this is a lot of the way Micronaut works internally. So for multiple data sources and so forth. We have, and a good example of this is data sources. So we have like a data sources. So for each SQL connection, we create a data source. So you can iterate using each bean and create a new bean for each configuration object, which is really neat. So I'll have actually another 2 beans here, pet configuration consumer, and we can verify that if you want. We can inject the configuration consumer, which will also be named 2. Second consumer, and it's really handy. Okay, so that's configuration properties, and each property and each bean, which are really cool for getting type safe config and binding them from your application classes. I demonstrated as well the use of @requires. @requires is really flexible. In that demonstration that I did, where I put @requires on something, pet service, I put like @requires here, and it was env equals environment test, something like that. That's just one way to use requires. So you can say @requires, this requires an environment of test, but you can also say this requires the property foo.var to be set to a value of baz, otherwise it won't load. You can say it requires the presence of another bean, some maybe pet configuration. So if pet configuration is not specified, then forget about it. You can do, there's a whole bunch of things you can do in here. Missing bean, but basically it's a very flexible way to define bean requirements. So a particular bean is only loaded under certain conditions. So Micronaut is very dynamic at runtime. That's the point I'm trying to, one of the things we wanted to achieve with Micronaut is not take away the runtime dynamicity, but just make it all statically computed at compilation time as much as possible. Okay, so I'm actually way behind on my schedule. So we may have to miss out on Micronaut Data at the end. But anyway, let's look at Micronaut AOP. And then in 10 minutes or so, 15 minutes, we'll have a break. So Micronaut AOP is designed from the ground up to be runtime and reflection-free, without the use of runtime bytecode generation, without the use of proxies, and fast and efficient thanks to smaller stack traces. So pretty much all frameworks out there, built on some notion of AOP. So the most famous AOP example out there, I imagine, is Spring @transactional, which is probably used in the most out of anyone out there. And then you got things like @cacheable and so forth. So the way traditional AOP systems work is that they, at runtime, they generate a proxy using the JDK proxies. Problem with JDK proxies is that one, they use reflection, so you're paying a reflection of cost there, and two, they only work for interfaces. So when they're not to support not interfaces, anything else basically, frameworks like Spring and so forth, you generally use a bytecode generation library at runtime. So they would use something like ByteBuddy or CGlib to generate a bytecode at runtime so that they can dynamically implement your class. So what's the problem with doing that? Well, the problem with doing that is that, as you get bigger projects and more classes and more proxies and more AOP usage, your memory requirements really grow because generating bytecode at runtime has a cost. Has a cost in terms of memory usage for the JVM. But before I get onto AOP, one fundamental usage of within frameworks is the usage of java.lang.reflect.method. So many frameworks out there get a reference to java.lang.reflect.method and then invoke the method using reflection. And like I said already, reflection is not the greatest thing in the world if you're wanting to achieve low memory consumption. So how can we get away with living without this feature, which has been so critical to Java's success and so forth? And the answer to that on the Micronaut space is, again, one of the kind of base framework features, which is @executable. So on any method you can add @executable, and essentially it will generate what's called a executable method reference. So for example, I could add @executable here, clean this up a bit. I could add executable here, and then I could inject the application context like this, and test executable, and doesn't matter how I spell it. And what you can do is get hold of the bean definition for that class, which would be pet service. And you can get hold of get required method. In this case, I think it's list pets. And that'll give you a reference to the executable method. So we generate a method that invokes your code, executable method. And and with this executable method reference, if you had an instance of pet service, so if I had an instance of pet service here, I could invoke it dynamically doing executable method.invoke pet service, and that would allow me to invoke and get the result dynamically, but without using reflection. So if there was another method inside here that did not have that executable, there would be no get required method would throw an exception. So there would be no. It only generates execution hooks for the methods that require dynamic invocation, rather than doing it for every single method like the JDK does. So that's kind of key building block. Now normally in a Micronaut application, you don't see @executable in a typical Micronaut application code base. You don't see it because why? Because it's used as a meta annotation. I'm going to skip that slide because I'm running behind. But basically, it's used as a meta annotation on other annotations. So an annotation on an annotation. And Micronaut AOP uses it extensively. So every single AOP type in Micronaut is annotated itself at executable. And there are essentially three types in Micronaut: @around, @introduction, and @adapter. @around, as you can imagine, allows you to decorate an existing method's behavior. So think @transactional, think @cacheable, think those kind of things. @introduction allows you to introduce new behavior to existing classes and interfaces. And Adapter allows adapting a method to a single abstract type. Now, that may sound confusing, but I will get to an example in a minute. So I'm going to quickly demo a round advice, and you will see how simple it is in Micronaut. But essentially what you do is you create, for example, I'm going to create a not null annotation, and it's going to be retention. It's going to be runtime, retention policy, where is it? Runtime, and it's going to be an @round advice. And I'm going to create a not null interceptor, and it's going to be a method interceptor. It's going to intercept my method invocation, and it's going to implement the method, and it's going to be @singleton. And initially, we're just going to call context.proceed, like that. Then in my not null annotation, I'm going to say this is of type this, because you can have multiple if you want. But this is going to be a not null interceptor type. And in my not null interceptor, what I'm going to do is I'm going to iterate over the method itself receives a context object. So I'm going to iterate over the parameter values that get received. So over each, or maybe I'll do an array iteration actually. Parameter context get parameter values. We can extract that into a local object array. So, and then we're going to do if parameter value equals null, throw new illegal argument exception, argument at index I cannot be null. So what we're writing here is a annotation that is a bit not very necessary because we already have things like bean validation. But basically, it's going to validate that no argument I can possibly pass to my method can be null. Then I may have like a, for example, a save pet method here or something of that nature. And what you can annotate with not null in that sense, and then when I would create a new pet and in here, and then save it somehow. So this is annotated with that null, which is my interceptor that I just created. So if I were to do something like test save and try to save the object with null, and I try and pass that in there, let's see what happens. So in theory, if my example is working already, so yeah, there we go. So argument at index 0 cannot be null. So as you can see, that is literally how simple it is to write AOP advice in Micronaut, right? There's no my fancy, wonderful proxy factory bean jazz gizmo going on that requires like complex bytecode runtime, bytecode enhancement, and weird things. It's literally just a compiler feature. And that makes it really fast and really performant. And what's really nice as well is just look at that stack trace. So this is this is the moment I invoke save pet until I throw the exception. And you've only got 3 frames of stack. Stack traces in Micronaut AOP and Micronaut in general, in terms of the core parts, are so much smaller, because there's no bazillion lines of AOP reflective logic, billion stack frames, and so forth. So that is literally how simple it is to write an round advice. It's basically what happens is the method gets intercepted. There's no runtime proxies involved. It's compilation time feature. No reflection needed. No bytecode generation. And a lot of Micronaut's internals are written in this way. They use a around advice. So, for example, this is a snippet from the retry interceptor that's part of Micronaut for doing retries. And yeah. So the second type of advice in Micronaut is introduction advice. So introduction advice is different to around advice in that you want to introduce new behavior. So where would this be used in Micronaut? So say, for example, you've got like a, I don't know, some interface. It doesn't matter. Particular. And then I wanted to write a something that stubbed out behavior. So let's write a stub annotation. Again, it's going to be just copy and paste this. It's easier than writing it. It's going to be retention runtime. In this case, it's going to be introduction advice. So we're going to introduce new behavior to something else, and it's going to be of type something. So let's create a stub interceptor, which again is going to be implement method interceptor. And there we go. And this is going to be a at singleton bean again. And so this is going to reference the stub interceptor. And we want to provide a value that we're going to stub out. Just default nothing for the moment. And so the logic that you may want to implement. So again, in this case, whilst in the around interceptor, if everything was fine, we proceeded with the original invocation. In the introduction interceptor, there's no behavior to proceed towards. So we actually have to provide that behavior. So how's this going to work? We're going to use the context object to get the string value of the stub annotation. So that's going to, or else it's going to be null. So that's going to be the value of stub, of the pass to the stub annotation. Then we're going to inject in here, in Micronaut, there is a conversion service object that provides type conversion facilities. So we're going to inject it in there. And we're going to do conversion service.convert the value of the stub to the context.getReturn type as argument. So we don't have to deal with generic types or anything like that, any business like that. Otherwise, we're going to return null. So that's going to be my implementation. So now I've got this interface, and I'm going to have a number method. I'm going to stub it out with the value of 10. I'm going to have another string method called name. I'm going to stub it out with the value of foo, and it's stub at the top level, so it's activated. And what we can do is create a test. Which is a Micronaut test. We inject my stub some interface. Just introduction. And so we do some interface dot name, for example, value set equals value. What was it again? Foo. And we run that. And if the demo gods are with me, this will probably pass. Otherwise, yeah, it does. So what we've done there is, so what have we done here? What have we achieved? We have an interface that doesn't have an implementation. Doesn't have anything that implements it. We have added an annotation that's going to implement that interface for me at runtime. And the actual implementation of the sum interface thing is produced at compilation time, and it gets intercepted. We retrieve the value of the stub annotation, which in this case will be 10. In this case will be foo, and we try and convert the value of the stub annotation to the return type of the method. Otherwise, we return null, and we've implemented this behavior. So that's pretty cool. We've implemented something that has an interceptor. So how would this be used in a real scenario? This is exactly how Micronaut's HTTP client works. So Micronaut has a decorative HTTP client that allows you to define an interface, add a client, and then have methods that get that implement the HTTP logic to do interchange between client and server, implemented for you at compilation time. This is exactly how it works, and it's a feature available to anybody who can use it. It's part of Micronaut AOP. So pretty simple. Again, you just define an annotation that has an introduction on it, and away you go. So I think that I'm going to stop there and let everybody. I've been going for an hour and a half, and let anybody who needs to have a break, and then we'll pick up again in 10 minutes and carry on with this in-depth tour of Micronaut's internals. Thanks. Okay, I hope you all had a chance to catch a breather, and it's been. I just realized I've got I got enough material here for like a 2-day course, so we're going to go through it quite quickly and hopefully keep you all entertained. So the last type of AOP advice I want to talk about is what I call adapter advice. And I'm going to do a quick demo of that because it's different to like introduction advice. So a common case in frameworks like Spring, like Rails, I imagine like Jakarta EE as well, is you have methods that are like need to represent another bean. So an example of that. Let's do an example of that. So say I had like a my processor interface, and this is a functional interface, and it's going to take my pet class like that. So we could define beans that my processor handled, and and get all the processes and invoke them and design a system like that. But often it's nice to be able to have in your actual classes a method that represents a processor. So how would you do that? What you can do is I'm kind of making this up as I go along. Create like a processed annotation. That again is retention runtime. So this is processed, and this is going to be an adapter, and it's going to adapt the my processor interface. So it's and then what you can do is you can say that this should be, for example, target. I think it's element type. Yeah, element type should only be applicable to methods. Yeah. So what we have now is an annotation that's applicable to methods that adapts the my processor interface. So what have we achieved by this? Let's have a look. So what you can do is I can say @processed void some method pet, and I'll put the pet. And then I can have another method, maybe called some other, that's also annotated @processed. And if I was to inject in here a list of my processor, like so, test invoke processes, iterate over interface, and call it with a pet called Bob. So first of all, I'm going to add an assertion here, assertion equals, because my expectation is that I'm going to have two of these guys. So let's have a see if this works out as I expect. So it did. So what I've achieved here is essentially every time Micronaut encounters an annotation called processed, in this case on my pet service, it's going to create a new bean that can invoke my pet service at that point. And it's going to implement the my processor interface. So where is this typically used, this kind of pattern typically used in frameworks? Well, the most typical usage of this pattern in frameworks, and it's used in many places, but the most typical usage is for events. So in Micronaut, what you can do is, instead of this kind of hand-rolled gizmo that I've done, you can say, oh yeah, and one actually nice thing I want to point out, because Micronaut is compilation time. Yeah, this is all compilation time handling. These methods have to conform to my SAM type, which takes a pet, obviously. It doesn't make sense if they conform to any other type. So, if I tried to put a URL in here, for example, and try to run it again, what will happen is that Micronaut's compiler will fail and say, I'm sorry, but I cannot adapt the method, some method, with called, to the target method call, which accepts a pet, because the type URL is not a subtype of type pet. So you get nice, ahead of time compilation errors instead of, most frameworks which would fail at runtime, saying, oh, this is, just an incompatible type error at runtime or something horrible. So you get early warnings of things failing. But in terms of how this is actually used, this is exactly how event listeners work in frameworks. So instead of this, what I can say is this is an event listener, and this is an event listener as well, and they both listen to the pet event. So an event listener is a Micronaut annotation that you can add. And then what I can do is in my test here, I can inject Micronaut's application event publisher. And I can say, event publisher .publish event new pet Bob, whatever. And you'll see that when I run this, I get my two events triggered through my event publication. So I've got decoupled event publishing capability within Micronaut. And it's nice because you can combine it with other Micronaut AOP. So for example, you can say on my pet service here, I can say that this event listener should be async. Then the invocation of that method will occur on the thread schedule thread pool that Micronaut configures. So you can annotate anything with async, and now you have async consumers of events. And with Micronaut Data, we also have, which I'll talk about later, we also have the ability to have transactional event listeners that only process an event if a transaction commits, for example, so that you can send a Kafka message only if your database commit actually worked and so forth. So that all works nicely in Micronaut, and you're not losing anything there. And that's how adaptive advice works. And if you look at the event listener annotation in Micronaut, the implementation of it, as you can see, all it is it's only got a couple of annotations on here. It's got adapter, application event listener, and indexed, because there's typically many of these. You can index them. And the event listener, application event listener interface is, again, it's another SAM compatible single abstract method interface, with one method called onApplicationEvent. So that is adapter advice, which is a really nice feature. And again, it's completely reflection free and so forth. So Micronaut's event listeners is a great example of adapter advice. You can adapt any single abstract method interface. You get nice early warning compilation errors if things go wrong. And moving on to more examples of AOP, we in Micronaut we built a version of bean validation into Micronaut itself. And the reason we did that was because, we found that Hibernate validator, which is the reference implementation of bean validation, one, it's like a 2.5 megabyte jar file, and it uses an extensive amount of reflection, the default implementation. And with that 2.5 megabyte jar file, we found when you turn that into a GraalVM native image, added like an additional 30 megabytes, or 25, I think it was, to the native image size. So that didn't help. And because it uses this extensive uses of reflection, and it had a lot of plumbing just to support all of that frameworky stuff that we're trying to eliminate with Micronaut. And this is the whole point with Micronaut, is that you can build much smaller runtimes by being more intelligent within your compiler. So with Micronaut bean validation, that's what we did. It uses the introspection API in Micronaut. The annotation metadata is all computed at compile time. The AOP part of Micronaut is all used. So you can come into any class like this, and I'll get rid of my homegrown version of not null that I wrote before, and you can say, this class is validated, and you can say, that you're using JavaX.validation constraints, but again, decoupling from that API, from the annotation metadata, so that when that rename occurs, it's just another annotation mapper. You're not going to have to worry about it. And you can declare not blank on your method arguments. And if I were to attempt to save my pet, and I'm going to inject my pet service again here, and try to save a pet service, save pet with a blank value, you will you will get a nice whoops, I have to run that test. You'll get a nice constraint violation error. The name parameter for save pet cannot be blank. So we have, Micronaut's validation, integrated bean validation is really a nice example of Micronaut AOP put into action. And we have full support for all the JavaX.validation annotations. It's only a partial implementation of the spec because we didn't implement the parts that require reflection. And we reuse Micronaut's existing bean introspections to make sure that we save memory, so that you don't have again my Hibernate validator, even within two projects under the same umbrella, Hibernate and Hibernate validator, you've got two different data caches, reflective data caches, one for Hibernate validator and one for Hibernate. The proliferation of these is the stuff of nightmares for me, trust me. So yeah, add validated, you can add onto any class the your validation constraints, and they get validated at runtime. And you can also go in. I'm currently validating a particular argument or pet in this case, but you can also go into the pet itself. Oh, I already have done. I've got these constraints here, and if I tried to, if I wanted to save an entire pet, in this case, you can say that this guy should be valid, and it will modify my test here to try and save a pet that's blank. And instead you'll get a validation error for the pet object instead, which is what I expected. So pet.name, the size must be between whatever and whatever, and in this case I got two validation errors. So which is what you would expect. So integrated bean validation as part, rolled right into the core of the framework, so that it's not a separate thing, and it's all packaged as one unit, and it's all integrated with the dependency injection container. And there's a whole bunch of other examples of Micronaut AOP that in usage throughout the framework. So you have things like cacheable, with support for Redis and in memory cache. In the cache project as well, we also got cache and something else in progress. At transactional, so as part of Micronaut Data, we actually support any you can use whatever annotation you want. If you want to use Springs at transactional, we just use annotation mapping to translate that. If you want to use javax.transaction.transactional, you can use that. We support at transactional in all of its forms. And retryable, so we support integrated retry and also circuit breaker, which typical in microservices to retry operations one or more times before giving up. And in the circuit breaker case, which is the circuit breaker pattern, it's a stateful retry where we cache the exception and don't attempt to retry for a period to avoid flooding the backend systems. You saw me demonstrate there at async, which is another usage of Micronaut AAP, which invokes the method running the operation on a completely different thread. Break time has already happened. So with that, I think I've more or less covered the core kind of DI, AOP, and parts of Micronaut that make it tick. Now we're going to look at the server, the client. We'll look at HTTP filters. We'll look at how we do things like Swagger, and we'll see how we go. So in terms of runtimes for Micronaut, there's actually, like I mentioned, multiple Micronaut runtimes. So the default runtime for Micronaut, I guess you would say, is the HTTP server, which is based on Netty, which is a reactive non-blocking server, but which also supports blocking workloads by offloading them to a worker thread pool, IO thread pool. We also support, Micronaut Kafka is a runtime by itself, where we support, headless Kafka processes, listening for streams of data and processing them with Kafka listeners. Micronaut, all of these, by the way, are dependency references, and also, I imagine, GitHub Slug references as well. Micronaut Pico CLI, which allows you to build command line applications with Micronaut, so using Micronaut DI. We also have integration with gRPC, so if you prefer gRPC, then to Micronaut's built-in Netty server, then you can go down that route, and we have support for both gRPC clients and servers, dependency injection with them. We have support for GraphQL, so integration with the GraphQL project, so that you can build, use Micronaut's DI and all of its pieces together with GraphQL. We even have other framework support, so we added support for Kotor, which is a Kotlin framework, which is in its little milestone phase, and we're still gathering feedback from the Kotlin community on that. And then you can go completely serverless and, just write AWS lambdas or, whatever function service. On the function side, we support all the container-based function services, function as a service platforms, whether it be OpenFaaS, as well as things like AWS Lambda. So let's talk about the default server then. So the default server, like I said, is a Netty-based reactive server with support for both blocking and non-blocking I/O. You can choose whatever reactive framework that you want to pair with it. You're not obliged to use RxJava 2 if you don't want to, but if you do, you got that as an option. You can use Reactor as well. It's basically anything that returns a publisher. It's just reactive streams based, essentially. You can bring your own annotation model, like I demoed in my brief proof of concept. For those JAX-RS fans, we'll probably be supporting those annotations soon. You can also use Spring annotations if you want. We have a project called Micronaut Spring, where you can plug that in and use Spring's annotations like @controller, @rest controller, and @get mapping, and all those kinds, and use those if you prefer. And we integrate with Jackson for with reflection-free extensions to Jackson, so that when you read and write objects to and from JSON, it's not using reflection. So I've already, probably without you maybe realizing it, I may have been demoing the HTTP server already. So this project, one thing about Micronaut test, which may not have been apparent already, but Micronaut test essentially spins up the server for every test run. So when I'm running this test, although I'm actually only testing my pet service here, it's actually spinning up the server. And we have it this way because one of the liberating things about Micronaut and how it's really like changed people's expectations for how Java frameworks should behave is that there's no real tangible speed difference between spinning up the server and not spinning up the server. So gone are the days where you needed to have like a separate source tree for your functional tests that because your server took like 10 minutes to load or start up, or 2 minutes to start up. There was a time not too long ago where people would choose to write more unit tests and less functional tests because functional tests were just simply too painful to write. Where if you have to wait 2 minutes for your server to spin up to run your functional test, people end up not bothering. Whilst in Micronaut, the functional tests are as simple and as fast and as productive to write as the unit tests. In fact, I can inject the embedded server. Micronaut has an embedded server interface, and into this test, and you can output the port, for example, where it's running, and that interact with it in whatever way you choose. If you have a HTTP client that you prefer that is not Micronaut's one, you can get a reference to the port. Notice how the port is 58498, whatever that is. So for test execution in the test environment, Micronaut will detect that you're running a test, and for the test environment, the port is set to a random available port. Sorry. Not a random number. It'll search for a available port and just use one that's available. This is a nice default because when you push your app into CI servers that run in the cloud or whatever, there's always something else running on port 8080 or having to figure it out. So it's nice that it's defaulting to that, but you can go into application.yaml, the right one this time, and you can configure the port by using Micronaut server port and hard-code it to whatever you want in here. But essentially, the default and then the default for the non-test environment is port 8080. Which is pretty common amongst Java servers. So other than that, do I have a pet control? I had written a controller here, which you can see. I don't even know if this controller still works. Probably not, because it was using other things. But yes, this is an example of a typical controller. The default behavior in Micronaut is that when you return a list of pet, in this case, it'll marshal those pets into JSON using Jackson. What's nice is how easy it is to write tests with Micronaut. So because of the built-in HTTP client, you can do things like write a pet client, which is an interface, and this is going to be a client interface, and it's going to talk to my pets, endpoint. And it's going to, let's make it a blocking one for the moment. Test list the pets like that. And in your service here, you can inject the pet client interface, and we can have a test list pets method, and we can do pet client.list pets. Get my results. Set equals to pets.size. And if the demo gods are with me again, that should work, which it doesn't, because the demo gods are not with me. Forgot something. Needs to get annotation. So we're going to get the pets on the root URI. There you go. That works. Okay, so as you can see, now there's no kind of obvious indication of this actually being a client-server test. It executes pretty fast. But what you can do is, in your logback.xml file, we default to logback, but you can use whatever logging framework that you want. You can say io.micronaut.http.client level equals trace, like so. And you can, if I run this again, you can see that we get the trace output for the communication. So this is actually the communication that's happening, within my test. So my client, in this case the interface, is making a GET request to the server, which is receiving it and returning JSON, and then I'm marshalling it back to JSON again in my service. Now, obviously, this is a blocking call. List returning a list directly, and generally it is not necessarily desirable, particularly for HTTP nowadays, which is really easy to write. Reactive logic. So instead of returning a list, you can, for example, return a flowable. And in my test, instead of what I'll get back here is a pet flowable instead. You can do toList, I think, blocking get, something like that, to make it back into a blocking call. And that will achieve essentially the same result. I'm now blocking again. Now, in real world scenario, you would typically, instead of doing this, you would do something like pet flowable subscribe, and have a consumer that listen to each pet event and so forth, and output it in whatever manner that may be. So you would have some kind of subscribe or non-blocking form of writing this. Now, in the case of a JUnit test, there's really no other way other than blocking. So that's not relevant. But another thing you can do as well is, even on the server here, on the server, I am returning a list of pet. Now, if this pet service that I'm writing is using some backend database driver, or maybe just communicating to another microservice, and it's a possibility to use non-blocking, then you can actually return a flowable from the controller as well. And here in my pet service, just make that go away. Instead, you can use flowable, not just for the moment. Now, I hate it when I see code like this in real life, where people are just using flowable.just and returning it, because there's literally like no value in this. However, other than adding complexity to your code base. However, in a real world scenario, I may have a Mongo client, or I may have be injecting my pet client in here in the constructor, and I may be making that call using a non-blocking flow. So making my client. You may be doing that and then mapping the data and mapping it to something else, accumulating, doing all those reactive things. Reactive is probably beyond the scope of this talk, and I imagine there's going to be a lot of reactive talks at this conference. But Micronaut is fully on board with the reactive programming movement, and it can certainly do all of the things that most frameworks that support reactive do. Like I said, there's another way that you can. Previously, I've demonstrated using application context.run, and there is another way you can do that as well. If you don't want to use Micronaut test, which is to use try with resources, so you can do application context.run and pass in a bean. It doesn't have to be embedded server, but it has to be a bean that implements, I think, managed context or something like that, and to make sure the context is shut down. In this case, embedded server does. And you can spin up the server programmatically using try with resources, get the port, and so forth. In my case, because I'm using Micronaut test to demonstrate everything, Micronaut test itself is spinning it up. But there's actually some really interesting integrations that you can do and interactions. For example, you can spin up, if you have a modular project and you publish each microservice as a library, you can actually spin up embedded Micronaut applications inside other Micronaut applications, if that makes sense, and have tests that communicate with each other, which is really nice because a Micronaut application in the end is just a library. So you can depend on some exported jar, and whether it be a test jar that you can then spin up locally. Obviously, in most cases, people typically mock out those kinds of interactions. But for example, where we've used this, Micronaut integrates with many different service discovery systems. So things like Console, HashiCorp Console, I don't know if you've heard of that, and Eureka. So instead of having to spin up Console or Eureka in some of our unit tests, which are quite heavyweight systems, for some of the unit tests, we actually wrote mock versions of those servers in Micronaut, and then spun them up in the same test, and the test itself is communicating with the mock version written in Micronaut. And then we have, integration tests that actually run them with test containers. Test containers, by the way, fantastic project. And with test containers, which obviously take much longer to run. But there's spinning up embedded servers in Micronaut is cheap, it's fast, and you can spin up multiple of them, which is handy. So controllers. All of the annotations for Micronaut are in the io.micronaut.http annotation package. You will find them if you're familiar with Spring, if you're familiar with JAX-RS, you'll find them you'll learn them in 10 seconds. It's it's not a mental overhead. However, if you are really, really opposed to learning a new annotation set, like I said, we do have Spring annotation support. We will have JAX-RS annotation support once we get around to writing the rest of those annotation mappers and so forth. And yeah, it's just an annotation programming model like any other one. So I've already done the demo of the HTTP client, really. So I'm gonna skip that. But essentially, the HTTP client in Micronaut is is Netty-based as well. So the server is Netty-based, and the client is also based on Netty. It features both a low-level API and a decorative compile time client, which the compile time client has what I just introduced. It uses that introduction advice feature that I demoed earlier to essentially, at compilation time, implement those interfaces. And we support, that's one thing I didn't demonstrate actually, is that we also support completable future as well as reactive types. So if you prefer completable future, you can use that API. It has built-in service discovery supports. So it's actually really, really easy to set up. Particularly with something like console, what you can do is you can basically do Docker console run console, and then port 855 something like that to expose port 855, and in the documentation for Micronaut. We have a whole section on the different service discovery systems that we support, including console and Bolt and Spring Cloud Config and AWS Parameter Store for configuration, and console and Eureka and Kubernetes and et cetera. But for console, you just run it, and you put this config in here, which is console.client.registration enabled. You point it to one or more console daemons or servers, and you run the app, and it will register automatically and deregister when it shuts down. And then for the client, you'll see that you got this Micronaut application.name hello world. That's the ID the service name that it registers with is this. So in this case, it will register with a service ID of hello world. And then what you can do is, like in the client interface. So if this was by prefixing this with the / here, I'm saying that I want to talk to the local server, like the local server. So it's only really useful for testing. But if this was not prefixed with underscore, this would become a service ID. So whenever my pet client is dependency injected, there would have to be a service discovered that had the service ID of pets around. Micronaut has a discovery client interface, which allows it to discover other instances. And one of the nice things as well is that we actually implemented this interface with Micronaut. What does that mean? So our Micronaut's console integration is written in Micronaut. Micronaut's Eureka integration is written in Micronaut. Why is that a big deal? That's a big deal because if you look at something like Spring or other frameworks, they typically pull in another 10 megabyte of jar files to pull in some specific console client or some specific Eureka client that's written in a different HTTP client, inflating your overall deployable unit size. Again, and creating bigger GraalVM native images, bigger jar files, bigger. So by implementing things in Micronaut, which means that using intelligent compilation, the runtime is smaller. We're able to do things like service registration whilst also keeping your application unit size small, which I think is really important. And we're doing the same thing with Kubernetes. So that we have a Micronaut Kubernetes project, which is available on Micronaut project / Micronaut Kubernetes, and it has support for things like K8s, config maps, and service discovery, and a whole bunch of features that make it nicer and easier to integrate with that ecosystem. So yeah. And the other thing is, you can see that this discovery client interface publishes one or more service instances. You see it publishes a list. It's a publisher that publishes a list of service instance. So why is that important? So if I'm referencing a service ID here, and what that means is that there may be 1, there may be 2, there may be 3, there may be 10 backend services that provide this service. And if you then start using retry, so if I added retryable here, if the first Micronaut will do client-side automatic round-robin load balancing. So if the request to the first service fails, it'll fail over and retry to the second service and loop and go through automatic, transparent round-robin load balancing. You can customize how the load balancing behaves as well. So there's APIs in Micronaut to fetch a service instance. So that if you look at the service instance interface, and it's got the ID of the service, the URI, but it's also got information such as the region, the zone. So you can write load balances, your own load balancing strategies, for example, that only load balance between servers in a particular region, which is quite common. You don't want to include servers that are on the other side of the world necessarily if you've got a broad system. So you can load balance between European servers or load balance between US-based servers or wherever your particular application is deployed geographically, which is nice. So that's all integrated into the way Micronaut works through the service instance interface. Okay, so 21 minutes left. So yeah, the client is. Another thing I should point out about the client before I move on, and about Micronaut in general, is that in Micronaut, every single annotation value that is a string is configurable. So what does that mean? What that means is I can put a value in here which is my pet service ID, otherwise pets. And I can have in here in my application.yaml pets service ID pets. And if I change this to junk, then the value of this value passed in here will be junk. So look for a service ID called junk for whatever reason. So that's because any annotation value in Micronaut this is part of the design of Micronaut. The annotation metadata is we made it environment aware and aware of your configured environment. So just by using the dollar syntax, now this is not like you can't put like weird expressions in here. It's not like a custom script or weird things. It's just a small deal. You can only really reference IDs and that's it. And the colon is used to separate what the default value would be. But you can even customize the pets URI mapping. Otherwise use slash. Every annotation value in Micronaut that is a string is configurable, which provides a lot of flexibility and customizability via configuration for your applications. Okay, so where was I? Okay, so the client again, it uses the other nice thing about the client is again we're using the same annotation set as the server. That means you can, for example, and some people do, create like shared interfaces that both the client and the server use, and then package clients that other services use that use the same interface, so you're not like duplicating things. So some people do that. Create like a hello operations interface that has the hello method, and then hello client extends that interface, and then hello controller extends that interface, and kind of sharing that in a type-safe manner. We also have this notion of HTTP filters. So, and this is done through the interface HTTP filter. So an HTTP filter is a little bit like a servlet filter, I guess you could imagine it, except that it's like a reactive interface where you have one method that is doFilter that takes the request and a filter chain, and you can proceed with the execution. And there are two sub-interfaces of this interface, one called HTTP client filter, and the other one is called HTTP server filter. And so what that means is you can write filters that run for both the server and the client, or just for the server or just for the client. So what would you use filters for? Well, there's lots of usages of filters, even within Micronaut. For example, we have support for cores, and this is implemented as a filter. So the other requirement for a filter is that it will be annotated with that filter, and which takes a pattern that it applies to. And you can see that the cores handling in Micronaut will, handle the origin headers and do all that business, and populate the appropriate headers prior to sending them to the response. So, and there's lots of examples within Micronaut of filters being used. Another example is our support for, Micronaut supports both Zipkin and also Jaeger through open tracing. So we have filters that support open tracing so that you can trace both client requests and server responses and so forth. So clients sending data, servers receiving data, and push all that data into your distributed tracing infrastructure. So filters are a key part of Micronaut and used in many different places to implement different things, whether it be security, tracing, and so forth. So another thing to keep an eye on. Micronaut, like I said, service discovery. We have support for console, Kubernetes, Eureka. We also have distributed configuration support for console, Kubernetes, Bolt, Spring Cloud Config Server, AWS Parameter Store, and native client-side load balancing, and tracing with Zipkin or Jaeger. In terms of management and metrics, there's a module for Micronaut called Micronaut Management, and you just add it as a dependency. And because it's written in Micronaut, again, it doesn't have a huge amount of impact in terms of memory consumption to your application by adding it. So much of the advice put out there to developers to reduce memory consumption in Java applications has been about taking away features. Yeah, you can get low memory consumption. You just have to take this away and that way and this away and this away and remove this and remove that and remove the next thing until your application is just hello world. No, that's not the goal with Micronaut. We want to be able to build real world apps that mean that you can continue to have features like management endpoints that expose health status, that expose information about your app, that allow you to mutate your log configuration, that allow you to look at the metrics that your application, and we support metrics via micrometer or micrometer. I'm not sure how that's pronounced. And you can see the environment, you can refresh the application, see your active routes, and so forth. So it's a very flexible module, and you can write your own endpoints as well. And again, completely reflection-free, and also GraalVM native compatible. So another nice feature of Micronaut is its support for Swagger. So you may have not noticed really, but whilst I've been running my application and testing my application, the compiler, the Micronaut compiler, has been generating a Swagger description for my microservice. So how does this work? So essentially, I have a couple of dependencies in my build. If you look at the build.gradle, you'll see that I have an annotation processor, an additional one for Micronaut Open API. So that's over here. So that's that annotation processor. Same thing in the POM. So in the POM, I've got the Micronaut Open API dependency. And as you're building your app, as you're compiling your application, Micronaut is using Micronaut's compiler APIs, which I showed you earlier in this talk, to generate your swagger.yaml, your open API description for your microservice, which you can then import into Swagger UI or a whole bunch of different client tools, auto-rest and so forth for generating clients. And it just works. And because it's processing the source code as well, we're able to share some of that source code information. So, for example, it'll actually translate Javadoc into your swagger.yaml definition. So why is this cool? This is cool because so many of the integrations in the Java space with Swagger, things like Spring Fox and many of the other systems out there, what they do is they do it at runtime. Yeah. So they analyze your classes and creating probably more reflective data caches via reflection, analyzing everything, consuming a whole bunch more memory, just so that you can expose some nice, Swagger documentation for your microservice. Yeah. Micronaut, on the other hand, because it's generating a static file at compilation time, there's no memory cost at runtime. It's just a static file that you expose to your users. Hey, this is my API. There's no additional runtime and analysis. There's no additional processing required. No additional cost of your application in terms of startup, in terms of memory. It's just a static file, and it's even intelligent enough to know that it's analyzed my pet class as being a component, and that it has a required property called name, and that it even analyzed the JavaX.validation annotations to figure out that the minimum length was 20, from those Java.x validation rules. So it integrates everything into the Swagger generation, just because everything is tied together in Micronaut. So that's a really nice feature of Micronaut, is the ability to generate Swagger automatically at compilation time without paying the cost of having some third-party component do it for you at runtime. So that it produces that swagger.yaml, and you can expose that file as a static file via Swagger UI. And again, doing the work at compilation time means using more intelligent compilers, creating leaner runtimes. That's what Micronaut is all about. And this particular feature uses the type element visit API, which I provided a brief demonstration of. Okay, so now I'm going to demonstrate a relatively newer feature of Micronaut, which is Micronaut Data, and talk a bit about, give a bit of an introduction to that and what it is, and also do a little demo of GraalVM native integration as well. So when we first released Micronaut, probably the most asked for feature that everybody kept asking us for was something like Spring Data, something like GORM, and or GORM, which is Grail's data access toolkit. And both of these solutions rely heavily on reflection and the creation of runtime proxies and so forth. And the way they work is they, at runtime, analyze your repository interfaces, so interfaces that you may define, and compute queries at runtime. And the bigger your application, the more this computational cost grows in terms of memory consumption, startup time, and so forth. And so when we looked at this problem, we were like, how can we apply the Micronaut way of doing things where we create this intelligent compiler to this space? And that's how we came up with Micronaut Data. So Micronaut Data is a database access toolkit. And what we do is, at compilation time, we visit your classes and pre-compute your SQL or JPA-QL queries based on your interfaces. And it uses Micronaut's reflection-free AOP, which I demonstrated earlier. I like to think of it as a zero runtime overhead database access solution, because you would literally find it hard to write a JDBC query faster by hand than if you used Micronaut Data. And because you have things like smaller stack traces, much smaller stack traces than a traditional stack, we can get significantly better performance. So if you look at the numbers out there, we have some benchmarks in the Micronaut Data repository. But for JDBC, you're looking at at the moment 2 times performance improvement over competing solutions. So we also were able to do, because it's a compilation feature, we're able to provide much more early warning when things go wrong. And I'll demonstrate that in a minute. So how does Micronaut Data work? So essentially, each repository interface that you define is annotated with, in terms of the JDBC implementation, is annotated with @JDBC repository. And you define an interface. And the interface defines methods that then get implemented for you at compilation time. So how would you perform CRUD? You call person repository.save and save entity. You call person repository.find my name to look one up. You can update people and you can delete them, and you have working CRUD. So let's see that in action, and how that works in practice. So I'm just going to close this project, and I'm going to open the JDBC example. So here I have a Micronaut with Micronaut Data application. And in terms of differences between this and any other Micronaut application, there is a couple. One, you can see in the build, we have an additional annotation processor, which is called Micronaut Data Processor. And we have a dependency on Micronaut Data JDBC in this case, and a dependency on a particular connection pool. So we support various connection pools. This is using the Tomcat one, but you can change this to Hikari or Commons, I think, pool is the other one we support. And it'll set up your database connection. And so that's pretty much it. And what you do is you define your sort of entity classes. For example, this is a pet, and it's using JPA annotations, but we support. We have our own. It has its own annotation model. But we support mapping the Java x.persistence annotations. So in this case, we have a pet entity that has an ID that's a UUID that's auto-populated by Micronaut Data. It has the many-to-one association. There's another entity called owner, which is annotated with entity, has an ID that's that's a generated value. You can create immutable objects, which I'm not in this. Well, name is immutable by using constructors and so forth. So that would be like my domain model. And because it's just using Micronaut's bean introspection underneath the covers, there's no need to like scan for entities like a traditional solution has to scan your class path. There's no reflection to read and write objects to and from the database. You can create like data transfer objects that are other introspected classes, which is pretty nice. And in terms of the repositories themselves, here's an example of one, or two, in fact. So we have a pet repository interface that extends a pageable repository, and it has a list method, which returns my name DTO. So the name DTO only contains the name property from pet. So it's only going to get the name property from pet, and not the owner and the type and everything else. And Micronaut Data is clever enough that it will generate a query that it only selects the name for the name DTO, which is pretty cool, or whatever other properties that you may define in there. You can find an individual pet by name, and we even have some basic support for doing joins. So you can join on a particular association in the interface, and you can just return optionals, find by name, or you can return the object directly. If you don't return an optional and null is returned, then you'll get an empty result exception, something like that. And you can see that in the repository itself, the dialect is set to H2 because I'm just using the HTML memory database, but you can switch it out. We have support for MySQL, for Oracle, for Postgres, for SQL Server. And so at compilation time, what Micronaut Data does is it looks at this interface and says, "Oh, I've got a find by name method here. Okay, that means I need to generate a query which is select select star from pet in this case, where pet.name equals name." It generates that query at compilation time, stores it in the annotation metadata, and then at runtime, all Micronaut Data has to do is execute the query. Retrieve the query and execute it, rather than having to wait till runtime to parse the meaning of find.name and figure out that and implement all of that. It doesn't have to do any of that, and it's also really smart in terms of compilation time checking. So here is first of all, let me show you this example here, which is, you can remember I was talking about the bean definitions. You can from the bean context, you can get the bean definition for pet repository in this case, and you can get the find by name method using get required method. So it's going to get the executable method for find by name, and you can get the string value of the query annotation. Which, there isn't one. There isn't a query annotation because Micronaut creates it at compilation time. And if I were to run this particular test, you can see the output. The system's output is within the annotation metadata. It stores the SQL query to look up a pet, including the inner join, because basically there's a join statement here. So the whole SQL statement is generated and stored within the repository bean definition. So what that means is all Micronaut Data has to do is get that query, execute it, and then translate a JDBC result set into individual entity objects, which is far easier because of Micronaut's being introspection API, where you can get and set properties and so forth. Also noticed how, so I'm running tests here, and this test is actually executing using my repository. It's spinning up my server using my repository, executing a find by name method for Dino, setting it's not null, doing some checks. And you can trace the query log here. You can see all the inserts and so forth it's doing. It's even creating tables and so forth. And the test runs pretty much instantaneously, even though we're setting up data sources, repositories, and so forth. So this is how we're trying to take Micronaut Data in a direction where it doesn't impact on your project in terms of memory consumption, in terms of performance, in terms of how it feels to run tests. Anything that is holding you back from being productive when you're writing your tests, you need to take a serious look at and think, is this really beneficial towards me? The other cool thing is, because it's all compile time, so if I were to misspell name, so find my name, and I tried to run this test again, you'll see that we get a compilation error. So every other framework out there that supports these kind of features would fail with some mysterious error at runtime probably. You'd have to wait till runtime to identify the error. And so here you're not losing any type safety. It's telling me down here that I cannot implement this repository method, find by norm. You cannot query the entity pet on a non-existent property called nom. Perfectly reasonable error message at compilation time, which doesn't leave you lurching in the dark about what's going on and what's going wrong. So, the actual pet repository itself, like I said, is extends pageable repository. So you can, which in fact in addition extends CRUD repository. So you can do things like already, like I can say assert equals. Well, I don't know how many there are actually, pets, but you can count the number of pets. Hold on. Don't think I ran the right test there. So I can count the number of pets, which there's actually 3 of them. You can list. The number of pets, when you want, page 0 and you want a maximum size, so you can paginate through the records by creating a pageable object, and that all works. And this list method is interesting because when I run this, you'll see that the select that gets generated, which is what I mentioned previously. The select is only selecting pet.name, and that's because the name DTO is being used as a return type. So you can project into selecting only a subset of the data by creating data transfer objects. And it's even smart enough that if I created another property here called blah, and generated a getter and setter for that property called blah. So obviously blah doesn't exist on the pet type. You can't possibly project on that type. Actually, that should have failed the compilation time, so I'm wrong. That's an improvement we need to make. That surprises me. Okay. So, but at least it failed at runtime with a sensible error as well. DTO projection defines a property blah that doesn't exist on root entity. So it should actually have failed at compilation time. Interesting that that didn't happen. Interesting. Huh? That's probably, yeah, I'd probably have to rebuild the whole project. You're right, yeah. Yeah, oh well. Okay, well, anyway. So you can, in addition to this, you can save a new pet in here. Jack, I don't know, owner is nullable. You can, to save in a new instance, you can find that person by ID. So Jack.getID to get it back, which actually returns an optional or null. You can then go ahead and delete that entity either directly or also by ID. Doing something like that. You can also do things like perform updates. So I don't have an example in here, but you can do things like void update pet update. Update by name, something like that, and where name is that, and then you can set the age or any other properties like the owner if they were settable. And Micronaut Data, because we're processing the source code, can see that these are the age and the owner property, and will query do an update only for objects with the name or with the name passed in there. So you can do like batch updates. You can do delete by name, those kind of batch deletes, and all sorts of things. And the performance always stays consistent. So with that, that's a little preview of, we haven't gone 1.0 with Micronaut Data yet, but it's at M4. But we will be 1.0 by the end of the year, and it's really promising, and people are really liking it. So now I want to talk a little bit about GraalVM and Micronaut. So GraalVM is a new universal virtual machine from Oracle. It has loads of features. It's production ready. The current version is 19.2 or 19.3 maybe, 9.2.2 or something like that. And it's got a whole bunch of features. It's got like replacement JIT for the normal Java virtual machine. It's got a truffle language framework, and it's got some really compelling language interop possibilities. And one of the features it has, which is just one feature of a whole suite of things, is it's called Substrate or native image. And this part of GraalVM is actually still experimental. So you have to install it as a separate component. It converts Java bytecode into native machine code using ahead-of-time compilation. And it works really nicely with Micronaut. So when we started building Micronaut, we had no idea that GraalVM existed, or was. I think it was open sourced about a month after we open sourced Micronaut, and somebody messaged me and said, "Hey, have you seen this thing? It does this AOT stuff and makes things consume even less memory." And I looked at it, and I looked at the requirements for making your application AOT or native image compatible, and they seem to me to fit Micronaut like really nicely. So because GraalVM's native image tool supports reflection, It does support reflection and has really good support for reflection. But you have to declare all the reflective usage and any runtime proxy usage upfront. So you declare it through a number of different JSON configuration files. And you have to tell it about all these usages of reflection. And so, because Micronaut doesn't use runtime proxies, doesn't use reflection, doesn't use dynamic class loading, doesn't use any of the things that you have to declare. Turns out it works really nice with Micronaut without having the additional configuration overhead. Not to say that you can't configure things, you can, but the fact that you don't have to makes them a kind of nice fit. And with GraalVM, these are probably conservative numbers. I've seen even better numbers with the newest version. I've seen it as low as 15 megabyte memory consumption and startup time as low as 15 milliseconds. But basically, once you've computed your Micronaut application into a native image, then you can get these kind of numbers, which from a Java perspective, is Java processes. So essentially, a Java application that consumes only 15 megabyte of memory. That's just like mind blowing for a lot of Java devs. I mean, we thought we did a good job getting Micronaut's memory consumption down to what it is, but then this is just like next level. So GraalVM is really cool. Substrate. The native image part is still in beta and experimental, but GraalVM itself is production ready. GraalVM optimizes, Micronaut optimizes for GraalVM substrate, but it also optimizes for regular Java, which is what most people use today. So I'm nearly coming to the end of my talk, but basically I do have a pre-computed native image of this application, which is using Micronaut JDBC, and you can see that if I run it with GraalVM, this is a full database access application that is using JDBC and everything, and the startup time starts up instantaneously, pretty much. And we can go to the pets, and we can go to the owners, and we can go to an individual pet. Dino, and this application is fully a full microservice application that is using JDBC. And in terms of what I had to do to get it to work on GraalVM native, well, not much, because there was a couple of things file to declare in terms of declaring resources, and I just had to do native image and point to my jar file, and it built. So I think that it's really compelling technology, and I think that there's serious improvements coming the way of the JDK and Java in general in terms of memory consumption. So keep an eye on the space because things will continue evolving. These are the kind of stats you can see, and it's very, very exciting technology. So, which brings me back to my original point with GraalVM native image. For me, the future is intelligent compilers and smaller, leaner runtimes, and that's where the whole industry is going. That's where we're going with Micronaut. I think that's where GraalVM is going. I think that's where other projects like Quarkus are going, and it's the future of Java. So I think I'm way out of time. So thank you very much. Micronaut provides awesome set of framework, and if you have any questions and you want to ask me anything, I'll be around down here. I probably can do a Q&A separate to this. I don't know.
Maybe here downstairs.
Maybe here downstairs. Okay. I do need to actually announce T-shirt winners. Do I have time for that?
Yeah.
Okay. So if anybody of you went and followed Micronaut, and you are still in the room, thank you very much. Well, we're definitely on the verge of 3K. a lot of extra followers. Okay, so who is Auke? Anybody? Okay. Okay, you have a free T-shirt. Okay, come up here. Who is, I don't know, Canoops? Free T-shirt. I don't know how many T-shirts I have, actually. There's at least 3. Okay, so who is Tizinia Trokins? There you go. Okay, free T-shirts.